Welcome students, and in this video we are going to talk about face portraits. Okay, first of all, what is a face portrait? Let's understand that. Face portrait. Now you have to understand this one. Since we are working with portraits, what happens is so essentially we are going to draw some pictures, and what happens is and these are for some particular curves. So you cannot go to higher dimension because we really can't draw those curves, right? So generally speaking, we are going to focus our attention to a 2x2 system. Okay, so first of all, let's say you are given this system, right? X prime equals to ax is given to you. Ax is the given system. Okay, and what is a given system with a being a 2x2 constant matrix, right? Being a 2x2 constant matrix. Okay, we want to see that how are we know that there are solutions to this, right? And essentially we want to see how we can so if there is any way to draw those solutions out, so we can see that how what their behavior. Once we do that, then we know that even for the nonlinear systems also we can do similar sort of thing. Okay, at least in a for certain type of equilibrium points and certain systems. Okay, that we already saw for nonlinear systems. So let's look at this. Okay, now if you remember, we talked about the canonical forms, right? So we can reduce all this 2x2 system. For 2x2 system, it's not very difficult. What we can do is we can reduce it into three different forms. So one is real distinct, one is distinct, and one is complex, right? So first of all, let's say that you have this system, and so this is case one. Case one. So we are looking for real distinct eigenvalues. Real distinct eigenvalues. Eigenvalues. Okay, so you have a 2x2 system, and essentially let's say you have a both the eigenvalues are real and distinct. Clear? Okay, and we are assuming that, let's say this is the case. So what are the three cases which can happen? You can have this one, right? Lambda 1 is between lambda 0 is between lambda 1 and lambda 2. The second case can be lambda 1 less than lambda 2 less than 0, and the third case is 0 less than lambda 1 less than lambda 2. Is it okay? Now you see the first case, we want to talk about the first case for now. So maybe I can start with the canonical forms. Okay, so the first canonical form is C. The first form A. Okay, so what do I mean by canonical form? You remember, right, that let's say you are given a constant coefficient matrix A, B, C, D, right? Let's say a 2x2 constant coefficient matrix is given. We can always have a change of variable under which we can reduce this to certain forms, right? You remember? If you don't, please go back to the videos where we talked about all this and then come back here. Okay, so what we can do is, there are these three cases. According to that, the canonical forms look like this. So first for the first one, it will essentially be looking like this: lambda 1 0 0 lambda 2. Okay, see why I am doing it, because essentially all systems can be reduced to this. So basically just to studying all the it's you just have to study the canonical form to study all the systems essentially, right? Okay, so first of all, let's say this form is there. This is the most easy, or natural form, right? So A is lambda 1 0 0 lambda 2. Okay, so that your you remember that diagonal form, right? And with the first part, lambda 1 is 0 is between lambda 1 and lambda 2. Yeah. Now, of course, you do realize if you can reduce this problem like this, then what happens is you can of course solve this system, right? Why? Because if you have something like this, it means that you have reduced the problem to lambda x1 prime equals to lambda 1 x1 and x2 prime equals to lambda 2 x2. Is it okay? Once this is there, you can solve this. This is like unrelated to equations, right? Very easy equations to solve. You can solve it, and what you are going to get is two different solutions. Okay, so let me just write it down. We already talked about it, so I'm not discussing those part. Let's just look at the solution now. So the solution in this case will look like this, right? xt equals to alpha e to the power lambda 1 of t, and then the eigenvalue. So in this case you can actually show that since lambda 1 0, lambda 1 and lambda 2 are two the eigen vectors. Yeah. So what we can do is eigenvalues. So what you can do is you can show that for the canonical form you have two the solutions, the eigenvectors corresponding to that will look like this: 1 0 and 0 1. Okay, beta times e to the power lambda 2 of t 0 1. Is it okay? Yeah. And once you do this, now you see, so that's your general solution. Is the general solution. Is the general solution. Okay. Now again, I'm telling you, if you do not remember how all of this is working, please go back to the videos where we talked about all these things. Yes. So of course, I mean, this sort of problems are very easy to solve. This is your general solution. So I'm not explaining that here, and we're just writing it down. Now the thing is this, see what is phase portrait. The main idea behind this video is this: we really want to look at, see this particular thing. Let's just look at this. See xt, if you just think about it, how xt looks like. Let's write down xt. See, for a fixed t, xt is nothing but this thing, right? x1 of t and x2 of t. Is it okay? I mean, you can just break it up like that, right? And this is nothing but, if you write it down, you see this is alpha times e power lambda 1 of t, and that one is nothing but this is beta times e power lambda 2 of t. Is it okay? And this holds for all t. So essentially, you see, you are basically looking at a curve, right, which depends on t. So basically this is a parametric curve. Yes. And what we want to do is we want to look at how are the solutions are. So basically how are these curves look like on a two-dimensional plane. So these are called planar. So that's why it's called planar system, right? Yes. So how does this curves look like? That's the whole idea of it. Okay, right. So maybe I can put it here. Let's just put it here. Yeah. So therefore this essentially, this is the thing. Hence xt is this for alpha beta in R, of course. Yeah, for an arbitrary alpha beta. Yeah. Now let's just draw some pictures. Again, the pictures may not be very nice looking, but you will get the idea of it. Okay. So let's draw the two-dimensional plane. Okay. Right. Now again, see, before I proceed with the diagram, so you have to realize one thing, that this is very rough. You understand? You don't have to be very precise with the diagram, but of course, I mean, it should at least give you a very rough idea, but I mean, kind of correct idea about how the trajectories of the solution looks like. Okay. So I mean, don't just draw anything you want. Okay, just you have to give so if you are solving a problem like this, you have to write properly that what exactly, why are the curves look like what they look like. Okay, so you have to explain everything. So I will do this part here. I will show you how it's done actually. Okay, so first of all, see, if alpha and beta, these are real numbers, right? So first of all, you have to understand, for this curve there is always an equilibrium. So any constant coefficient 2 cross 2 or 3 cross 3 system, doesn't matter, any constant coefficient system like this, homogeneous system, right? And there is always an equilibrium point. So if you consider, so note, there is a small note. Okay, so if you consider f of x, yeah, you remember, let's say this is a of x in your case, right? And you do see that 0 0 is always an equilibrium point, always an equilibrium point, right? Equilibrium point. Yeah, irrespective of whether A is, invertible or not, doesn't matter, but 0, 0 is always an equilibrium point. And let's say if there are like two distinct eigenvalues, in this case it is right that lambda 1 is less than 0, which is greater than less than lambda 2. Essentially, in this kind of case, you do realize that you have you may have this sort of thing that A is invertible, and then what you have is 0, 0 is only equilibrium point. Okay, so in this case you see the only equilibrium point is 0, 0. Okay, so equilibrium point is basically, now the question is this: we want to see how the trajectories behave near the equilibrium point. That's the whole idea of this course, right? Yeah, so how, let's look at that. See, what is happening here is this: first of all, alpha and beta is any real, right? So let's say if I am assuming alpha equals to 1 and beta equals to 0, you are basically looking at e power lambda 1 t 0. So basically you are looking at this sort of thing, right? Xt is e power lambda 1 of t and 0. You understand? Now you see, please don't start drawing anything. You see what is happening is this: this is a curve, right? So xt and yt, yeah, and what does this doing? It is e power lambda 1 of t and 0. And this t is varying in r. Okay, so t is going from minus infinity to plus infinity. Yeah, now you think about it. See, for a fixed t, so let's say t equals to 1, let's say, this is just a motivation. You don't have to write all these things. I mean, this is how you start. You see, if lambda t equals to 1, what happens? What is e power lambda 1 t? It's basically a real number, right? So with this particular point, let's say, so let's say t equals to 0, let's say, t equals to 0. This point is nothing but 1, 0. So see, it is somewhere here. 1, 0. Let's say this is 1, 0. Okay. Now you see, if t, so lambda 1 is negative here. You see, it's given lambda 1 is negative, right? So if lambda 1 is negative, since lambda 1 is negative, you see, as t tends to infinity, what is happening is this particular point is going towards, this particular thing is going towards 0. You understand? So essentially this vector approaches the equilibrium point 0, 0. You understand? So essentially, as t tends to infinity, you see, from minus infinity, this is the arrow which will indicate where the trajectory is going. So basically this is one of the trajectory, okay, along this line only. So what does it mean? One solution look like this for a particular choice of alpha beta. Okay, and you see it goes towards 0. You understand? It's going towards 0. So basically, as t tends to infinity, this goes towards 0. You don't have to draw this particular line. This is, I just draw it for the purposes. This is 1, 0. Okay, at t equals to 0, it is somewhere here, and after that, as t tends to infinity, it is going towards here. At t tends to minus infinity, you see, this is actually blowing up, going towards minus infinity 0. So basically, it is coming. So it is coming from here, minus infinity. Let's say this is a large n 0, right? As t tends to minus infinity, so it is extremely large. It is going towards minus infinity, right? So it is coming from here. The trajectory is coming from here, and it is pushing towards 0, 0. You understand? That's the idea. So the first trajectory looks like this, and really, to be very frank with you, you really can't draw it properly because it is merging in the y-axis. So y-axis is a solution in this case, right? Okay, sorry, x-axis is a solution here. Right. Similarly, you can also see that, let's say, if alpha equals to minus 1 and beta equals to 0, you have a similar sort of thing, but in the other way, this way. So this is another trajectory. You understand? So let us draw it like this. Maybe I can use a different pen. Let me do it this way. I hope you understand what's going on. You see, all of these are going towards 0, 0. Okay, it cannot cross 0, 0. Please understand this. This is one trajectory. This is one solution curve. Okay, the other solution curve is this. Yes. Okay, right. Now the thing is, what about similar thing is if you are taking alpha is 0, beta 1. So you see, if alpha equals to 0 and beta equals to 1, yeah, what happens is you are exactly having the similar sort of situation, but in the y-axis, right? So you see, you have similar sort of situation, but in y-axis. You see, this is what is happening, right? See here. Yeah. And where is it converging? Again, same. Now see, here lambda 2 is positive. Here lambda 2 is positive, right? So you see, in this case, x of t is alpha, first I'm taking a alpha to be 0, right? So basically this is 0 and this one is e power lambda 2 t. Okay, lambda 2 is positive, so as t tends to infinity, okay, this actually blows up, right? And as t tends to minus infinity, this goes to 0. So you understand, we'll look at the trajectory as it starts at minus infinity, and we'll look at what happens at t equals to infinity. You understand? So you see, in this case the trajectories, they are moving away from origin, right? So it is starting from very close to origin as t tends to minus infinity. From minus infinity, it's going away from the origin in the y-axis, that along the y-axis, right? Because all these points are in y-axis. You do realize that, right? As a t tends to infinity, since lambda 2 is positive, e power lambda 2 goes to infinity. So basically this is going in this direction. Is it okay? And similarly here also this is going in this direction. This is going in this direction. Is it okay? Yeah, you don't have to draw all these double arrows. This is an example I want to emphasize what is happening here, and that is why we are doing it. But generally speaking, when you do this sort of thing, you draw at least one arrow, okay, just to signify what is happening, and the arrow will actually be in the direction from minus infinity to infinity. We are going to look at what is happening at to the trajectory from minus infinity to infinity. So arrow points this way. Is it okay? Of course, you can put double arrows, that's not a problem, but this is just an idea. Okay, now the thing is this, see, how do you, see, this is for a particular choice of alpha, beta, 1, 0, 0, 1, that sort of thing, right? And, but alpha and beta both can be, non-zero, right? Yeah. In that case, what do you do? That's the question. Okay, so first thing first, see that in any other case, so if, let me put it this way, if alpha beta both are non-zero, okay, then all other solutions, they tends to infinity also. Okay, by the way, I forgot to mention this. You see this line, all the trajectories are moving towards the equilibrium, right? So we actually call that line, since they are moving towards the equilibrium, we call that line as a stable line. Okay, please remember this thing. And this line where it is moving away from the equilibrium, we call it a unstable line. Is it okay? Now you see, if alpha and beta is not equals to 0, you can see that all solutions, let me write it down, all solutions, okay, we are looking for what is happening to the solutions as t tends to infinity. So tends to infinity, okay, in the direction of unstable line, right? Direction of unstable line. What do I mean by this? Okay, see, let's write down xt is e power lambda 1 of t and e power lambda 2 of t. Is it okay? Now let's say alpha beta non-zero. Let's just look at one trajectory. Yeah? We're not really interested in all the trajectories, just one trajectory. Let's just look at what is happening. If alpha and beta are 1 and 1, so x of t should look like this, right? And what is happening is this. So please understand this, all of these trajectories are individual solutions of this system. Is it okay? Right, now you see xt equals to e power lambda 1 t and e power lambda 2 t. Lambda 1 is negative, lambda 2 is positive, lambda 1 is negative, right? Now we want to see how does this trajectory looks like. Okay, now as t tends to infinity, you do realize, see, sorry, when you start at minus infinity, very close to minus infinity, that is, okay, since lambda 1, you see, since lambda 1, this particular lambda 1 is negative, right? So at minus infinity, this particular coordinate blows up, right? Yes. And what about this coordinate? This coordinate, if you just look at it, you see, at minus infinity, very close to minus infinity, that's when you are starting out, this goes to 0. You understand? Okay, so see the trajectories as t tends to minus infinity starts very close to, see the y-axis is 0, you understand? Yes, the y-axis is 0. Okay, and when when this t tends to infinity, you see these solutions are getting very bigger and bigger, but this is going towards what? You see, this is towards so as t tends to infinity, what did I say? This is minus, so this is going to a 0 infinity kind of thing, right? As t tends to, you understand? So basically it is converging towards an this line, stable line, you understand? Okay, so what is happening is this: for a large enough t, okay, the solutions are starting very close to, so as t tends to, see again, let me clarify again what I am trying to say here. See, as t tends to minus infinity, okay, so what I'm saying is t is negative, extremely large. Yeah, let's just look at this. Where is this point? So where is this point? More or less a rough idea. Lambda 2 is negative, right? So it starts from very close to this is negative, very close to infinity, right? This converges to infinity, and this particular thing converges to 0. Lambda 2 is positive, t going to a minus infinity. Okay, so this starts very close to, I mean, minus infinity 0. So here you understand, at t tends to minus infinity, and you see at t tends to infinity, what is happening? T tends to infinity, this goes to 0 infinity. So basically you do realize it will be somewhere here, you understand? Okay, so it is very, I mean, kind of it is merging towards the unstable, this y-axis. Okay, so the solutions look like this. Okay, you understand what's happening? And see, this is minus infinity to infinity, so the arrows will point here. I hope this is clear. See, as t is very large in the negative direction, so t tends to minus infinity, these points, if you can see, they are tending towards infinity 0, right? Kind of. So what does it mean? They are actually very close to the x-axis, right? Yeah, the x-axis. And what happens? So very close to x-axis, see, and after that, as t tends to infinity, it is becoming asymptotically, I mean, going towards the y-axis, because it is going to 0 infinity, you see, and that is why the arrow points this way. Okay, okay, so once you are done this, you can just draw another curve, doesn't matter. Now you don't have to be very precise with it, don't worry about it. Okay, it's just to give you some idea, you see. Okay, so another curve like this. Yeah, again, my drawing is not very nice, but you do realize what's happening here. Okay, and similarly, how do you feel? So once you are done this, you see, for now you can take alpha negative, beta positive, similar sort of thing will work. So essentially you have this sort of thing. Okay, you have this sort of thing, and the arrows will point like this. Here also you will have similar sort of thing. Okay, and the arrows will point this way. I hope this is clear why it's happening. And again, here also you can actually guess which side the arrow is. Not guessing, I mean, you can just see symmetry, right? So essentially it will go this way. Okay, so this is for different choice of alpha beta. If one is, let's say alpha is always negative, beta is positive, alpha both are negative. Okay, so in that case you are here in this particular quadrant, you understand? So all these solutions are there. Now you just draw those solutions. That's the thing, you just draw it out, and it doesn't have to look very pretty. You can just give you it should just give you some idea. Okay, now the question is this: see, why we are calling this, I mean, this sort of situation. See, origin is there, right? This is the origin, and you have this situation that along this direction, along some direction, yeah, you are approaching origin, along the other direction you are actually going away from the origin. Yeah, this sort of situation you already know from several variables. We call such a situation as a saddle, right? So you see, 0 is a saddle point in kind of thing, right? Situation. So this particular picture, the portrait which we draw, is called a saddle face portrait. Is it okay? It's called a, so let's write it down. This is called a saddle face portrait. Saddle face portrait. Okay, why saddle? You have seen the horse saddle, right? So what happens is along some direction you are reaching the maxima kind of, the critical point where you are sitting essentially, yes, the point of contact. And the thing is along another direction you are essentially reaching a minima kind of, right? So that's why it's called saddle, right? Okay. Now where do we have yeah, so this is one situation. Okay, now you can of course take an example and just draw it out, but that is for assignment, so I'm not doing that part, huh? So let's look at the other case. So this is the form A, huh? There is a different form, let's just call it form B. Okay, so what happens is if both are non-zero but there are different signs, then you have a saddle. Okay, now we have another situation. This situation we are going to look at this. See, you have two signs, lambda 1 less than lambda 2 less than 0. So basically two eigenvalues are there, both are negative. Is it okay? And then your solution x of t, again I am not explaining this, you know that this will look like this, alpha times e power lambda 1 of t, again 1 0 plus beta e power lambda 2 of t 0 comma 1. Is it okay? Now we want to see how the trajectories looks like. Let's just draw some pictures. Okay, let's just draw some pictures. So again I am explaining you one thing. Do not worry about how the don't draw whatever you want. Okay, what I'm trying to say is try to draw the best you can. It doesn't have to be precise. The idea is not have to be, it should not be a precise diagram. It's not possible, right? But the thing is you can just give you just by looking at the portrait you can just understand that what is the behavior of the solutions, huh? How is the flow moving, you understand? See, think about it. In this picture, if I'm saying that if I'm putting a point here, you understand? Now I want to see what is the evolution of this point. Essentially what it is saying is this. See, this particular thing and with this initial condition, so our initial condition is this point, let's call that point x naught t naught. So let's say it is x naught y naught, that point, huh? So x of t at t equals to 0, let's say this is your initial position of the particle. What this is saying is this is actually giving you a kind of vector field, if you can think of. And what is happening is this, if you put a point here, yeah, think of your magnetic field, yeah, that sort of thing. If you put a point here, that point will be carried out. So there is this flow lines going, you understand this? Think of an invisible magnetic field. There are like flow lines, right? These are also flow lines. See, essentially what happens is if you put a trajectory, a point here, that point will be carried along this trajectory, you understand? It will be carried along this trajectory, and so it will go from this side to, it will go along and it will converge towards the unstable. If you are starting with a point here, what happens is that point will be forced to go towards the origin. If you are starting from a point here, that will be moved away from the origin, it will be thrown away from the origin, you understand? Yeah, so this is kind of the evolution, the flow. We want to look at what is the flow of a particle. If you put a particle anywhere in this thing, see, all of these points are moving, you understand? So if you put a particle there, it will actually, we want to see what is the behavior of the particle, how is it evolving with time. Okay, so that is what phase portrait does. Okay, so now let's again look at this particular thing. You don't draw this x, y and put this comma, these arrows, here. Please don't do it, otherwise it will get confusing, just do it like this. Here also I did it, but you don't do this arrow thing, don't do it. Okay, so just put this x, just write it as x and y, don't put that all these arrows, it will get confusing. Okay, now again what we have is this. Let's say if you have something like this, you can write it as alpha e power lambda 1 of t and beta e power lambda 2 of t. Now you do realize again, depending on whether alpha beta is positive or negative, of course lambda 1 and lambda 2 are both negative, we actually have to draw our curves. Okay, so first thing first, let's just understand this. You see, if both alpha, see, first of all, alpha is positive, beta is negative, yeah, or let's say beta is 0. Alpha is 1, beta is 0. Let's just understand that. Then what you have is the first coordinate is the second coordinate is essentially 0, right? And as t tends to infinity, if lambda 1 is negative, you do realize that the points will converge towards the 0 0. So essentially see here, since both are negative, you do realize that all solutions tends to 0 0 as t tends to infinity. Yeah, note. So I don't have to explain to you this one part, right? You do realize that at t tends to infinity, since lambda 1 and lambda 2 are both negative, all these vectors essentially they are pushing towards the origin, the equilibrium point, right? Equilibrium point is this. So essentially what it is saying is this: see, if you are drawing a vector face, so basically if you are drawing the face portrait, it actually says that if you can put any particle, so it will actually resemble that particular vector field, where if you put any particular particle, that will get forced into, I mean that will actually, you know, it will go towards the equilibrium point, you understand? So kind of a you understand, it's basically attraction going on, okay, and everything is coming towards the origin. So we call this sort of thing as a sink, you understand? We call it a sink. Sink means you do realize everything, every trajectory is sinking towards the origin, okay? So that's why it's called a sink. Okay, so first of all, the first solution, you do realize it will look like this. So I'm not using a different color. You do understand that this is one solution. Of course the solution cannot cross 0 0, you understand that, right? So it will be very close to 0 0. This line is a solution. Again similarly the other part will also be there, okay? And what about the y-axis? See, initially this particular thing, y-axis is moving away, right? But here this is not the case. It has to move into the equilibrium point, because all the solutions are tending towards 0 0, right? Because both are negative. See, this is happening, okay? Now, so these are the solutions, at least for one coordinate 0, another one is 1, right? So that is there. Now the thing is this: let's say that if alpha and beta are both non-zero, yeah, how do you draw all these other curves? Let's just understand. So what is the general trick? So how do you do that? What you do is, first of all, you want to see how, the question is this: how do they approach the origin? You do realize that the face portrait won't look like this. See here, what is happening is this: in one direction it is moving towards the origin, in other direction it is moving away from the origin. So even the linear combinations, when alpha beta non-zero, they looks like this, yeah, depends on which one is dominating based on t, right? Which coordinate. Here what is happening is this: see, every solution, doesn't really matter where you are starting. So basically it may happen that you are starting from here, right? And what happens is the trajectory can move like this, you understand? It can move like this, it can go towards the origin, it has to, right? Again it can start from here and it can go like this, you understand, and go towards origin, you understand? Now the question is this: what is happening? So in which direction then? This direction, like this, something like this, or something like this, you understand? We want to understand. Or it can go towards this, okay, yeah. So or in a straight line also, it can go like in a straight line, right, towards the origin. So we want to figure out what is happening, yeah, how is it moving towards the origin, okay? So to do that, you see, what we are going to do is we are going to write down dx2 by dx1. Let's just look at it. So basically, given any point, the curve, we want to look at the slope, you understand? Okay, so what is the slope of the solution? Okay, so that is given by dx2 by dt, okay, divided by dx1 by dt. Is it okay? This is your general usual thing, so I'm just writing it like this. So that is nothing but lambda 2 beta e power lambda 2t by lambda 1 alpha e power lambda 1 of t. So that is given by lambda 2 by lambda 1 beta by alpha e power lambda 2 minus lambda 1 times t. Clear? That's what. So the slope, what it is saying is this: given any trajectory, the slope will look like that. Yes. Now since lambda 2 minus lambda 1 is positive, right? It's positive. See, lambda 1 is less than lambda 2 minus lambda 1 is positive. Since this is positive, all these slopes, okay, approaches plus minus infinity. Why plus minus infinity? Because it also depends on the sign of alpha beta, right? That will also change. See, lambda, this particular thing, lambda 2 by lambda 1, this particular term, this is always going to be positive. Both are negative. Lambda 1, lambda 2, both are negative. So that sign is always going to be positive. Now, depending whether beta and alpha, they are positive, negative, you can have any sign, right? Because they are like, how do I put it? Alpha beta non-negative, non-zero, sorry, but they can be negative positive, right? So it can be negative positive. So the thing is, at t as t tends to minus infinity, see, this is positive, lambda 2 minus lambda 1. So as t tends to infinity, what is happening is this: e power lambda t goes to infinity, and depending on the sign of beta and alpha, it will actually, the slopes will approach plus minus infinity. Is understand? Okay, so that's what I wrote. I hope this is clear. So this is a sink. Let me write it this way. Okay. Approaches in plus minus infinity. Okay. Now the thing is this: how is it approaching? See, again, we understand that it is approaching to is approaching plus minus infinity, but how is it doing that? Okay. See, these solutions, if you look at this, these solutions, okay, tends to origin, tends to the origin tangentially to the y-axis. Okay, so essentially what it is saying is this: it is tangential to the y-axis. So when it moves, see, as t, lambda 2 minus lambda 1 is positive, t is how do I put it? T is starting from, so we are starting t. So at minus infinity, this particular term, e power lambda 2 minus lambda 1 times t at minus infinity, this is going towards 0, right? Yeah, if you think about it. So the slope is kind of like this, you see, parallel to x-axis, kind of, at minus infinity. And you see, as it tends towards infinity, yeah, the t tends to infinity, the slope is parallel to this. You understand? It's parallel to y-axis. So you see, this, the curve should look like this, no? You understand? Okay, so this is the idea. See, the curves will look like this. Okay, and similarly this, and similarly this. Okay, and similarly here, this also, this and this. Okay, sorry, here, you see, it is coming towards origin. Everything is going towards origin. So the arrow looks like this. I hope the idea is clear here, what is happening. Okay, see, this and this. Is it okay? I mean, the picture is not very pretty, but you do realize what's happening here. Okay, so that's the idea. Okay, so now you see so this is called a sink, because every solution is basically moving towards the origin. You can put a particle anywhere, and you know that the particle will end up, you know that the particle is going to end up near the origin, okay, as t tends to infinity. So that's the situation with sink. Okay, and there is another thing, form C. Let's say, what is form C? If lambda 1 and lambda 2 are both positive, they are distinct and positive. Okay, in that case, what is going to happen? You see, I mean, this, please check this part. You have to do it yourself. Check it. You have similar phase portrait, right? Similar phase portrait. face portrait. But let's just understand what's happening. You see, the similar sort of situation will, whatever we did for the sync case, same sort of thing works. But the thing is, in that case, see, lambda 1 and lambda 2 are positive, so this particular thing will be positive depending on beta alpha. This is also similar sort of thing, exactly same. So the face portrait, this trajectories will look similar. Okay, nothing changes. But the thing is this, see, as t tends to infinity, if lambda 1 and lambda 2 are both positive, then the solution is moving away from origin. You understand? All solutions moves away from origin. So here you have to note, all solutions move away from the origin. I hope you understand what is happening. Okay, here in the earlier sync case, everything is moving towards the origin, and here every solution is moving away from the origin. Is it okay? So if that is the case, see, then origin, if you can think of, everything is originating at the origin and moving away. So basically we call such a situation as a source. You understand? The initial situation is sink, in this case it is source. So what you do is this is part of the checking part. So what you do is, please go to the drawing board and please draw some portraits of this particular case. Okay, see how it works. Exactly the similar sort of thing, but the direction of the trajectories are reversed, right? Okay, so more or less I hope the idea is clear. So let's say if you are given a general 2x2 system, and if you have two distinct real roots, what you do is, you can of course change it to a canonical form. That's like very easy to do, right? Please do that, and once you do it, then you know that this will be either in this form or in this form. So this is one of those, at least it can't be anything more, right? Okay, now let's look at the complex eigenvalue case. Okay, now things are very easy. See, that's the general idea. Let's just draw some curves now and understand. So the first case is this, form A. You have this system, x prime equals to x, right? X, yeah, and your A in the first form will look like this: 0 beta and minus beta 0, if you remember. Okay, and of course beta is non-zero. Okay, now you see the characteristic polynomial in this case. So if you want to just write down what is the solution, let me just recall. First of all, you have to look at the characteristic polynomial, and you get the eigenvalue, which is plus minus I beta, right? And then corresponding to that, you find the solutions. So please check this part. Check that you can show that the solution here, x of t, the complex solution will look like this: e power I beta t 1i is the complex solution. Now if you remember, you see, the thing is, we told you that here we are working with real systems. Okay, so we are not going to look at complex solutions. Now this is a linear system, so you understand that if a solution, let's say here x of t looks like this, right? x1 of t plus I capital X2 of t. Yes, if this is a solution, that's a linear system, you can show that both x1 of t and x2 of t are going to be your solution, and they are real valued, right? Yes. Okay, so all these theories we already did. Yeah, so I'm not going to do all that. I'm just going to write down what the general solution is. Yes. Again, if you don't remember all this, please go through it again. Okay, so what is the general solution in this case? X of t is c1 times x1 of t, which is, let me write it, it is cosine beta t minus sine beta t, okay, plus c2 times sine beta t and cosine beta t. Okay, that's your x of t. It's okay. Now you see what I need to do is this. We need to draw some curves. We need to draw these curves. Now, you see, these curves are really easy to draw. You do realize that these are nothing but circles, right? These are nothing but circles, yes? So let's look at this. See, the thing is, first remark, let me just put some remarks here before we go to the drawing part. Remark. You see, each of this trajectory, okay, each of these solutions or trajectory, whatever you want to call it, each of these solutions is a periodic function, right? Why periodic? Because it basically is sines and cosines, right? So it's periodic. And what is the period? It is 2 pi by beta. Huh? So it is period with period 2 pi by beta. Is it okay? Now you see, so if you want to draw the pictures, let's just draw the curves. How does it look like? Okay, so see this, as I told you, I mean, but you also know, right? If let's say c1 is 1 and c2 is 0, yes, so what are you going to get? You are going to get a circle. So you are going to get some circles, and please excuse my drawing, but you do realize these are circles. Okay, these are circles. Okay, circles. Now, what happens if C1 is 0, C2 is 1? Similar, same thing. You see, this is a circle. Again, if C1 and C2 are both non-zero, then also you can see that they are going to be a circle. I mean, nothing changes. Okay, so essentially, what is happening is this: these are all these trajectories are essentially ending up becoming just circles. Okay. Now, the thing is, circles is fine. So this is the easy case, right? Just circles. Huh? Now, the thing is, see. Again, 0 0 is the equilibrium. 0 0 is the equilibrium. That is always there. Equilibrium. And all the trajectories are just circles. So what does it mean? It means that if you put a point here, so it will move radially around the origin. You understand? It will maintain the same distance from the origin. It will move around indefinitely. As t tends to infinity, it doesn't matter. So it will just moving around. Okay. So now the point is this, but it can move in a counterclockwise direction or in a clockwise direction. Yes. How do we get that part out? How do you know that is it moving in a clockwise direction or counterclockwise direction? Okay. See, I have a point, right? And this point is on this vector field. I want to see that what is happening from minus infinity to infinity. Now I understand that they are moving in circles, but how? Whether it's counterclockwise or counterclockwise. Now, so please check this part. This is let's put it this way, hash. Let's put the hash. See that the circles are transversed okay, in a clockwise direction, right? In clockwise direction, if beta is positive. I hope this is clear. I will explain to you why this is. Okay, and counterclockwise direction, if beta is negative. Is it okay? Now, so why is it true? But you can just take one example and just see. You don't have to worry about everything, because it's basically, I mean, after change of variables, it's basically the same thing. So it's essentially a circle. Now, let's say that you look at this cosine beta t and sine beta t. Let's look at this particular thing. Okay. Now you know how to draw this, but let me just go through it. You see, at pi by, so first of all, let's just look at t equals to 0. Huh? See, the trajectory, once you look at what happens at t equals to 0, you will now look at as t equals to something which is more than 0. So you understand in which, direction it's moving. At t equals to 0, this is 1, 0. Right? So at t equals to 0, it is somewhere here, let's say. Huh? Maybe here. This is a unit. This is the unit. So 1, 0, somewhere here, t equals to 0. Okay? Now, I hope so. T equals to 0 is 1, 0, right? Yeah. And t equals to, let's say, beta is there, right? So, pi by 2 beta. Okay? Beta is positive. Beta is positive. So, this turns out to be cosine pi by 2 and sine pi by 2. Cosine pi by 2 is 0 and this is 1. So, this is here. Okay? Pi by 2 beta. So, this is cosine pi by 2 and sine pi by 2. What is cosine pi? What is cosine pi by 2? Cosine pi by 2 is 0 and sine pi by 2 is 1, right? So it is 1. Okay. Am I doing it correctly? Let me just see. Yeah. So as t tends to infinity, what is happening is this: as t tends to infinity, this is going from 1, 0 to, I hope everything is correct, right? Whatever I am doing. As t tends to 0, at t equals to 0, this is cosine 0 is 1, 0. So at t tends to 0, it is 1, 0. And at t equals to pi by 2 beta, beta is positive. Yes, beta is positive. So this becomes pi by 2, cosine pi by 2 is 0, I hope. And sine pi by 2 is 1. So it is coming from 0 to, see, as t tends to infinity. So basically we want to see increasing t. T at 0 is 1, 0. And t at pi by 2 beta is 0 and 1 here. So you see, this is moving in this direction. You understand? Yeah. So we can draw this particular thing. Yeah? So this is in counterclockwise direction. Okay. Maybe I wrote something. This is mistake, right? One second. Let me just look at it. Sorry. There is a minus here. I missed that minus. Sorry. Yes, I'm really sorry. Yeah, we missed that minus. So it is cosine beta t minus sine beta t. So you do realize that here it will be 0 minus 1. So you see, it's a circle. It starts from 1, 0. At t equals to 0, it is this. So as t is increasing, t equals to pi by 2 beta. Beta is positive. So it goes here, right? It goes here. So you see, it is moving towards this. That is why it is counterclockwise. Sorry about it. Sorry for the confusion. So this goes towards. So please look at the signs. Otherwise you will get confused. So this is clockwise direction, beta positive. Okay. And similarly, all other curves also will follow the same thing. Yeah. So you just have to draw it like this. Now you do realize that if beta is negative, you can just do this thing, but in the opposite direction. Okay. Right. Now let's look at the second form B. This is a little complicated. Okay. So what happens is, in this form you have your A, which looks like this. So this is please understand, these are all canonical forms which I am writing. Okay. This is not any form but canonical form. If you have a problem initially which has a complex eigenvalues, you can actually have a canonical, you can reduce it, right, to a canonical form which will look like either A equals to 0 beta minus beta 0, or it will look like alpha beta minus beta alpha. It's okay. This is A. Now here alpha beta is not 0. Yes. Now we want to draw the curve. So maybe I can do it in the next page. It will be better for me. Next page. Let's do that. Okay. So case B. Okay. So what we have is this. See. In this case again, what is the general solution? No, again, I am not solving it here. I am just writing the general solution. That will look like this. C1 times e power alpha t and cosine beta t minus sine beta t plus C2 times e power alpha t sine beta t and cosine beta t. Is it okay? Now, you see, without the e power alpha t term, this is the case, right? If alpha is 0, you don't have e to the alpha t, and this is the case, right? So, we have the center. This is the center. We call it a center. Okay, because everything is like centered, right? Now, in this case, what we have is this, but if alpha is not 0, yeah, if alpha is not 0, then e power alpha t, what it will do is it will turn these same solutions, yes. So the solutions with alpha equals to 0, what is happening? The solutions are moving in circles. You understand? With alpha not equals to 0, the e to the alpha term, they will turn this solution into spirals. Yeah. So the solutions, this, please again check this part. Check this part. It is good for you. In that case, you will get a very good idea of what's happening. The solutions, okay, they converts the solutions trajectories. Okay, sorry, maybe I can write down the trajectories, and it's better. The trajectories spiral into the origin, okay, when alpha is negative. You understand that at alpha negative is what is happening is this. Initially the points are just every point, whatever they're always on the circle. Now here what is happening is this, the points, they will start somewhere here. You understand? See, as t alpha, let's say, is negative, so as t goes from minus infinity and towards infinity, if alpha is negative, they goes towards the 0, right? You understand what is happening? But kind of a circular, because of this cosine sine thing, they are very much like in a circular fashion. So something like this is happening at minus infinity. See, since alpha is negative, let's say, then e power alpha t, that is minus infinity, right? So it is coming somewhere from minus infinity. Now, how is it coming towards origin, that we will discuss later, but for now you understand this is coming from minus infinity, and it is, springing, kind of a spring, so it is going towards the origin like this. Okay, now going towards the origin, there are two cases. See, it can go in a clockwise direction, it can go in counterclockwise direction, it can go in clockwise direction. You understand? Towards the origin, go towards the origin like this, towards clockwise or counterclockwise. Okay, first of all, again, since alpha is negative, t is negative, let's say, towards minus infinity, so e power alpha t is positive. So basically, sorry, not positive, it is towards infinity, so basically it starts from my infinity somewhere. Okay, and what is happening is this, as t tends to infinity, alpha negative, so e power alpha t is going towards 0. So you understand, all these trajectories are moving towards 0. Yeah, but the thing is, they can't move like this. You understand? They can't move like this, they can't move like in a straight line. Why? Because this particular terms are there, alpha, cosine, sine thing, the periodic terms are there. And what these terms are doing is this, essentially they are actually pushing it back towards, kind of, this particular terms. See, of course you can just draw it out and write it, but the thing is, intuitionally speaking, what cosine and sine is doing is, it is actually forcing the solutions to stay very circular as possible, right? Depending on alpha. But the thing is, so, but alpha is forcing it to, move towards or away from 0. Okay, so that actually, if you want to draw it, and please do that part, check that part, you can see that they are basically trajectories which are moving towards 0 if alpha is negative. Now the thing is, again, as it is moving, it can be counterclockwise or clockwise. We are just trying to figure that part out. Okay, so what are the things? So it is spiral into the origin when alpha are negative, and away from origin as alpha is positive. I hope the idea is quite clear to you, right? Okay, so let's draw the pictures here now. Again, as I told you, you don't have to be very precise about it, but at least try to give a general idea of how the solutions may look like. Okay, so see, the thing is, this is this sort of situation, this particular situation, we will call it a spiral. You see, everything is coming towards the origin, so it is sink. It is called a spiral sink. Is it okay? And this particular situation, this is called a spiral source. Source, why? Because everything is moving away from it. It's basically a source. The equilibrium is here also the origin is the equilibrium, right? So it's basically a spiral source, means that it's moving away from the origin. Okay, it's source. It's basically a source. Okay, so how does this drawing looks like? Let's just draw it. So essentially, again, at minus infinity it is infinity, huh? So it's just moving like this. Again, my drawing is not very good, but you to realize what's happening, huh? So it is coming like this and moving towards the origin. Okay, moving towards the origin. Okay, now yeah, I hope this is fine. Yeah? And it is moving towards the origin. See, towards the origin like this. Okay, so here in this case I drew it in a counterclockwise direction. Okay, so see, why is it counterclockwise? It doesn't have sorry, I drew it in a clockwise direction. It is moving towards the origin, converging to origin, but in a clockwise direction. Okay, this is the drawing which I did. Doesn't have to be, it can be in a counterclockwise direction also. Okay, now the question is this: how do you actually gather in which direction it is moving? Okay, so what you do is this: let's say you take a point, okay, on this how do I put it, plane. Okay, let's just call 10 point. Okay, see, if you are putting it this xt, huh? Alpha beta, this depends on what alpha beta is, right? See, if you have a point here, the point will move depending on the tangential direction, right? And that is given by the equation. See, x prime equals to x ax, so it means x prime of t equals to a of x of t. You understand? See, what is happening is this: let's say t equals to 0. Yeah, if you just look at t equals to 0 here, so at t equals to 0, what is happening is e power alpha t is 1, and you can just write it down what that point is. Okay, see, what is happening is this: let's say that the point, the trajectory, the matrix is this 1, and let's just say beta is again 1, and my beta alpha is 1, beta is 1, right? So this is one form. This is the matrix for which that is negative. And let me give you an example on how to calculate this particular things. Okay, so that's your A. Now the thing is, you see, I want to see that what this matrix does to the point 1 0. You understand? 1 0. See, let's say that I start my particle at the point 1 0. So basically x0 equals to 1 0. You understand? Now in that case, I can see what is x prime of 0. It is nothing but a x of 0, which is a times 1 0. Yeah, in this case, what is a times 1 0? It is 1, and this minus 1. Is it okay? So in which direction is it I mean, for this particular day, this is actually looking at 1 minus 1 direction. You understand? 1 minus 1 direction. The vector is pointing towards that, whatever direction that is. Now, so you do realize that depending on that direction, you can actually see that whether this is, I mean, clockwise or counterclockwise. At this direction, let's say it is, I mean, for example, let's say here you see, since alpha beta, I did not write what alpha beta is, I mean, not a particular example, so I really can't draw the direction here. But you do realize in this case, what is happening is at the point 1 0, the direction it is showing is 1 minus 1. Okay, so basically this sort of direction. Okay, so you see, if a trajectory starts from here, it has to move like this. You understand? So you understand? Okay, so depending on the direction, it will actually show which way it will move. Okay, as t increases, so that will actually give you whether it moves in a clockwise direction or a counterclockwise direction. I hope this is clear. Put a point on the face plane and see what is the tangential direction. That will actually show you that in which direction the tangent is. So essentially that will give you the idea of in which direction the curve is moving. Yes. Okay, so I hope the complex case is fine with you. Now we have the difficult case. What is the difficult case? The difficult case is the repeated eigenvalues case. Okay, so repeated eigenvalue. What is the repeated eigenvalue? So basically in this case, let's say your matrix A looks like this: lambda 0, 0 lambda, okay, and lambda of course not 0. Okay, now the thing is we want to see how the trajectory looks like. So now I really don't have to explain to you how all of this works, right? The general solution, because we have already talked about it. I'm just writing down what is the general solution. So in this case the general solution will look like this: x of t is e power lambda t 1 0 plus c1 times plus c2 times e power lambda t, if you remember, t1. So this is a vector 1 0, but this vector is t1. That is little different. That's the general solution. Yes. Again, if you do not remember, please go through it again. Very very important that you know how these things work out. Plus c2 times t e power lambda t. So if you write it down, it looks like this, and then it is c2 times e power lambda t. Okay, this is the thing. Now you see what is happening is this: if I want to draw the face portrait for this particular thing, let's just draw that. I'm not going to draw everything here. I'm just going to give you an idea. See, if C2 is 0, yeah, if C2 is 0, and let's say lambda is negative or lambda is positive, doesn't matter, lambda is negative, let's say, it can be negative also, right? Okay. If C2 is 0, what is happening is this particular term and this term is not there, so you actually end up with C1 e power lambda t and 0. You understand? Yeah. And so essentially, depending on C1, you can actually draw the peaks, and since lambda is negative, I'm assuming, so you understand that will actually push the trajectories towards the origin. For lambda negative, I'm just drawing one part. I hope this is clear. Let me just write it down, otherwise you may get confused. So note, for lambda negative, every term of the solution tends to 0, right? Each term of the solution tends to 0. Tends to 0 0. Okay, tends to 0 0. Yes, and of course it is, see, C1 e to the power lambda t, C2 e to the power lambda t, it is quite clear that it is going to a 0 0 if lambda is negative. As t tends to infinity, it goes to 0 0. But what about t e power lambda t? See, this is t e power lambda t also goes to 0. You have to understand that. Why? Because you see, lambda is negative, t tends to infinity, e power lambda t is the dominating term, right? Dominates t. So this also is true as t tends to infinity. How do you prove it? You use L'Hopital. Okay, please use L'Hopital to show this. So essentially what is happening is we can show that for lambda negative, every solution is tending towards 0 0. Okay, and of course if lambda positive, similar sort of thing is happening, but it is moving away from 0 0. Okay, so check for lambda negative, solutions move away from 0 0. Is it okay? Now the thing is this, we want to see that what happens to this case when C1 and C2 are non-zero. Okay, so this part I want you to check yourself. Please check this part. Check. If C1 and C2 are both non-negative, non-zero, then the solutions solution tends towards or away from origin. Why tend towards and away from origin? See, C1, C2 is both non-zero, let's say, but lambda can be positive, negative, right? If lambda is negative, of course they tend towards 0, 0. If lambda is if lambda is negative, they tend towards 0, 0. If lambda is positive, they move away, right? So that is always there. But the thing is, since C1 and C2 are both non-zero, how are they moving away or going towards the origin? Say they do it in the direction tangent to the vector eigenvector 1, 0. Okay, origin in a direction tangent to the eigenvector 1, 0. Vector 1, 0. Okay, how am I getting this thing? You remember we did this analysis initially in the first case. You see, we did this analysis, right? The slope analysis. Okay, you also do the slope analysis here. Yeah, please do this part. You do the slope analysis and show that the solution, basically what happens is they actually the direction, yeah, they are tangent to the eigenvector 1, 0. So basically tangent to this particular the x-axis. Okay, so what is happening is this. See, the solution will look like this in this case. Okay, sorry, my drawing is really bad, but okay, and similarly here also it will look like this. Yes, I mean, you see, moving in, moving away. So let me just do it for lambda negative. So this is for lambda negative case. Okay, this is all moving in towards the origin. Okay, moving in towards the origin. Yes. See, as you can see, the direction, the direction. So basically, how is it tending? The tangential direction is in the direction of 1, 0. You understand? So you see, it is tangential towards 1, 0. So it looks like this. That's the idea. Okay. And of course, if you want to just look at what some initial points what they are doing, you just put t equals to, let's say, 0, and let's put some t positive some number and see how the trajectory moves. If you really can't determine what exactly should the trajectory be, so you do that. And now this is general idea, but you do realize that the whole curve will be the whole plane will be, I mean, filled with this sort of trajectory. So basically, let's say if you are starting somewhere here, how do you move? So essentially you move tangent to the, you see, you move tangent to the eigenvalue 1, 0. Okay, so basically you go like this, and after that you come here. You understand? And similarly here also, if you start somewhere here, you end up doing this thing. I hope this is clear. Okay, so please check this part. It is not very difficult, and of course you do not go on drawing the whole lot of thing. Just draw 2-3 curves in either side of the plane and you are more or less done. Just to give an idea. Okay, so what happens is, here you see, since if you have a if you have a matrix which is invertible, 0, 0 is the only equilibrium point, and then you just draw everything around 0, 0. You understand? We just want to look at what is happening around 0, 0. Now let's say if you have a nonlinear system or a very, I mean, complicated linear system, what happens in that case is there may be different kind of equilibrium points, and in that cases we talked about this stable equilibrium, this stable manifold theorem, you remember. In that theorem we talked about how trajectories behave near the equilibrium point for certain matrices, right, for certain particular matrices. And the thing is, so they are basically linear systems, right? So once you know how linear system trajectory works, you can actually draw a complete idea of how the trajectory works in a nonlinear system. So around the trajectory points, how are the vector fields working? Is it okay? You understand? Okay, so that's the more or less the content of this. And please go through some different examples and try to figure it out yourself. I think this will be, it is not a very difficult thing to do. You can of course do this thing. Okay, so with this I am going to end this video.